yes, then I officially don't have an X.
Right.
You say, I don't know what you're saying.
What is y'all?
All right, questions? All right, we're going to do lots of proofs.
Yeah.
Yay. All right, induction, whether we call it weak or strong, simply is really, for us, we would have to ask, when to use. If you have one, your propositional function. Two, a universe of discourse that is countable. And three, you want to show that for all n, p of n. So for everything in the universe of discourse, something is true. And we can't do it. So if these things happen, that you have something that you want to show that this is always true type of thing in all of these cases, so some sort of propositional function at all, sometimes it's hidden in kind of an awkward way. But in the end, it's a statement about a universal statement that has a universe of discourse that's countable. So we have a first, a second, a third, a fourth as we go through it. If that's true, then we should be able to just go ahead and use induction. The two types that we have, again, are weak induction. Induction proves for all n p of n by rather breaking it into a two-part problem. We have the basis step, basis case, which is simply show p of the first element is actually true. So the propositional function evaluates the true for the first element that we're looking at. And then the weak inductive step is assume p of the kth step. This is called the inductive hypothesis. And then show p of the k plus first step is true. In other words, what you've done is you showed that p of k implies p of k plus 1 is logically true. By a direct proof. So we assume the inductive hypothesis, and we're going to use the inductive hypothesis in some sort of fashion to show that the k plus first version is also true, which means we've proved the implication, which is what we wanted. These two things, right, the basis case and the weak inductive case, together with a larger tautology, means as a byproduct for all n p's of n. So that just kind of falls out for us. So we've turned it into a two-case problem. Case one, the basis. Case two, the weak inductive. The only difference between weak induction and strong induction the basis is the same. We still do the same thing for the basis. But on the other hand, first element might be a little bit, we have to kind of think sometimes a little bit harder on what the first element is. But the strong inductive and our strong inductive looks like this. The strong inductive case becomes assume that p of the first and p of the second and everything up to p of the kth elements So for each of these, the first element, the second element, the third element, and the kth element are all true. We assume all of those are true. And then we're going to show P of the k plus first is therefore true. In other words, what we've done by doing this, we've actually showed that P of 1 and P of 2 and everything up to P of k implies P of k plus 1 is true. So we've proved this implication if we simply assume the left. Again, the left is still, this is all the inductive hypothesis. Notice how there really is no functional difference between the strong induction versus the weak induction. The strong induction says we have all of them. The weak induction says just worry about the last. Well, obviously the weak induction is the special case of the strong induction. We're just going to take everything from the first element, all the way up to the kth element as we do it. So whenever we do these sorts of proofs, they're all the same thing. We are going to have a basis case. We are going to have an inductive case. And by proving those two things, this comes about, the for all n p of n comes about as a byproduct of a larger tautology that I'm not going to write down, right? We wrote that down last class. It's like, oh, by the way, that must be true because we have a different tautology that we know exists. So it really comes to a induction proof is a proof by cases. We have two special cases, right? The basis and the inductive case. So if we can do that, we've showed for all NP of n. All right, what I had you hand in. So example for the attendance. If you have a 2x2 board, a 4x4 board, all the way up to a 2 to the n by 2 to the n boards, right? So these are my objects. They're obviously, this is my universe of discourse. This is the thing I'm talking about. It's obviously countable. It's the first, the second, the third. It's well ordered. My propositional statement is P of n. My propositional function is a 2 to the n by 2 to the n, where n is equal to 1, 2, 3 board with one missing piece. Can be tiled by that particular shape. So if it's 2x2, 4x4, 8x8, I don't care as long as it's a 2 to the n by 2 to the n shape. If I take one piece out, I'm guaranteed that I'm going to be able to tile it with these little L-shaped tiles. All right, we're going to do this by induction. And so proof. This would be a very good example. Could you possibly see these being done in general without induction? Just simply say, okay, you have no such thing as induction. Just assume that you have a 2 to the b by 2 to the b. Now tile it. Physically tell me how you're going to tile it. You'd have to try to find some sort of universal process. It's like the idea of solve ax squared plus bx plus c equals 0. You had to use techniques, you know, completing the square, extracting the square root, to form the quadratic formula, right? You're just simply doing all of them at the same time. The only way to do this directly would be to say, I have any 2 to the n by 2 to the n shaped board. I remove one piece. And then for every single one of those, I'm going to have to figure out a way to tile it with these L-shaped pieces. Well, how many of those boards even exist? And how many ways could I possibly tile it? There's no approach to that to just simply do it. And so for all NP of n, it's too difficult. So what we'll do is we'll rather do induction. So we go to the basis. Is this true for P of, what's this first object that we have, right? We have a 2 by 2 board, right? That's actually n equal to 1 is 2 by 2. Is it true that I can tile a 2 by 2 board if there's one piece missing with an L-shaped piece? Well, if there's one piece missing, it actually forms 4 things. It will either look like this with this missing, or it will look like this with this missing, or it will look like this with bottom right, or D. Same thing, but now it's the bottom left. Can all of these be tiled by an L-shaped piece? Yeah, I would just simply go through this and say, oh look, I would use the L-shaped piece here. I would use the L-shaped piece in this position. I would use the L-shaped piece in this position, and I would use the L-shaped piece in this position. And so all 4 forms can be tiled. So, true. It's at least true for 2 by 2. All right, now we're going to go on to the inductive. What do we assume? We assume we can tile a 2 to the k by 2 to the k, which would look like this, right? That would be a 2 to the k, and that would be a 2 to the k board, with a missing piece somewhere, with one missing piece. Doesn't matter where the missing piece occurs, it's just that it has a missing piece. I just assume that I can tile it. What's my goal? Right. Which means show that we can tile a 2 to the k plus 1 by 2 to the k plus 1 with one missing piece. Right, that's what my goal is. I know that I have the inductive hypothesis here. There's my inductive hypothesis. I know that's true. Okay, let's look at what is a 2 to the k plus 1 by 2 to the k plus 1 actually look like. If I have a board that is 2 to the k plus 1 by 2 to the k plus 1. But I know that 2 to the k plus 1 is simply 2 times 2 to the k, but that's equal to 2 to the k plus 2 to the k, right? That tells me each of these sides form 4 inner objects, and there's a missing piece somewhere. I don't know where. But this is a 2 to the k, and this is the 2 to the k. Is everybody okay with that? All right. So 2 to the k plus 1 by 2 to the k plus 1 is 4 2 to the k by 2 to the k. And one of those two to the k by 2 to the k have a missing piece, and 3 do not. Kind of important. So I have 4 2 to the k by 2 to the k's, but one of those is a 2 to the k by 2 to the k with a missing piece. What does my inductive hypothesis require? it says I can tile a 2 to the k by 2 to the k if it has a missing piece. So that would tell me that, so 1, the missing piece, 2 to the k by 2 to the k, can be tiled. That's the inductive hypothesis, right? So that means this part here, let's go ahead and blue it out. Doesn't matter which one, it's one of them. But then I know that 3 are full. They have no missing piece. So what I'm going to notice is that what about the other 3? Those look like a big giant L. Every one of which is a 2 to the k by 2 to the k. So what about these other 3? The inductive hypothesis says that they have to be missing a piece to be able to tile them. So if I went in here and, say, took out a piece and took out a piece and then took out a piece, out of each of those, would I be able to tile the 3? Yes. Well, instead of just randomly picking, well, I didn't have this piece, and I didn't have this piece, and I didn't have this piece, I can tile them all except for those pieces, except for one piece. If we look at it, is there 3 places I should take so that an L-shaped piece would actually cover all 3 pieces? The shared corners. If I would go in here and say, I don't care, any missing piece will work. But if I was smart, I could say, you know what? How about I take this piece out? Will the lower left be tileable by the inductive hypothesis? Yes. Let's take this piece out. Will the lower right be tileable by the inductive hypothesis? Yes. Let's take this piece out. The upper right would be tileable by the inductive hypothesis. And then, so that's what we would do. We would, okay, take out one piece of each from the common corner. And then guess what? Inductive hypothesis says all 3 with piece missing can be tiled. So then what you've done is you've tiled everything else except for the red. And so there's one last thing for me to do, and that shouldn't have been the number 3. That's number 2. And what would be the third thing that you would do to finish this proof off? You would just simply drop one L-shaped piece on the shared corner. Good to go. What's nice about inductive hypothesis type of problems when we're using induction is not only does this say that I can do it, it actually gives us a technique to do it. For example, how using this idea of the guy who is missing a piece can be tiled, the others remove the corner, and then I tile each of those, right? What would that mean for a 4x4? What if I did a 4x4? Physically, I'd go ahead and just simply do it. So 1, 2, 3. And I have, say, this piece here. That piece is missing. How would I tile it? Step 1 would be what? Cut from a 4x4 to a 2x2. Who do I first tile now? the one with the missing piece. So I would go ahead and tile the one with the missing piece. Then what would you do? I would just simply tile this corner, right? And those are a missing piece. And now what do? Go for each of them and tile them completely. And so you would say, oh, look, that means that this, and then this, and then this. So if you're a tiler, and I give you L-shaped tiles like for this floor, and there's one piece out here that's missing, I simply say, well, that one block must be red because that's where the teacher stands. And this room is 16 by 16. Could you tile it with these L-shaped pieces? Sure. What would you do? You would cut it into 8 by 8. But then which of those ones do you focus on first? The 8 by 8 that's a missing piece. But then how do I tile an 8 by 8? You cut it into a 4 by 4 and then tile the one that's missing a piece. But how do I do a 4 by 4? Cut it into a 2 by 2 and then start going away from the one that has a missing piece. And then you just simply go, you handle that 2 by 2 and then you handle the other 3 2 by 2s and now you're at a 4 by 4. Then you handle the other 4 by 4s using the same idea down to 2 by 2s and then outwards. And then you're done with an 8 by 8, but then I got 3 more 8 by 8s to do. And how do you do that? Go to an 8 by 8, turn it into 4 4 by 4s, turn each of those 4 by 4s into 2 by 2s, and then you just work your way back out. Would it look, it'd be a very interesting tiling job, right? How many people have tiled? Right? Normally what do? You start usually when you want to start and then move away. What would this do? You'd be constantly jumping to where that special tile is and building away from it and then going to the next guys and say, well, this is the center and then moving away from it. It'd be kind of an interesting look. Hopefully you wouldn't have any twists at all. Make a nice weird problem. But that's how you would tile it. It gives you not only a proof, but an actual way to do it physically. All right. Most of these problems are numeric. Let's say I wanted to have that 1/2 plus 1/4 plus 1/8 plus 1/16 plus everything up to 1/2 to the n. All right. It's going to be equal to something. Well, let's see what it equals. See if we can make a formula for this. All right, what are my n's? What are n's starting at for this object? 1, 2, 3. Let's look at it for a second. I don't know what this is equal to. I'm going to try to get a formula, but from this formula, then I'm going to try to prove my formula. So the first thing I want to do is make a conjecture. Figure out what it is. For n equal to 1, I just have what's on the left? 1/2. So I bet my right side is going to be a 1/2. Right? For n equal to 2, what's my left? 1/2 plus 1/4. But that is 3/4. Okay, that was 1/2. For n equal to 3, that is 1/2 plus 1/4 plus 1/8, which is, what's the common denominator? 8. And all those together are 7/8. That's a pretty good, I believe I know what my P of n is going to be. I'm going to say that P of n denotes that 1/2 plus 1/4 plus everything up to 1/2 to the n becomes what? What's the denominator? 2 to the n. And then what's the numerator? If I wanted to, I'd actually write this as rather this. 1 minus 1/2 to the n. I like that one a little better. Because what is your last object? An 8th. What's your answer? 1 minus an 8th. What if I went up to 1/16? 1 minus a 16th. What's the limit of this as it goes to infinity? 1. This particular problem is a geometric problem, which, there's always issues of people do this forever. What do you get? That people used to struggle with. Like, shoot an arrow, at the back of the room. Well, for the arrow to get to the back of the room, it has to get halfway there. But then it has to get halfway there again. Then it has to get halfway there again. Every motion to get halfway there takes a certain amount of time. To get halfway there again takes another certain amount of time. So what am I doing? I'm adding an infinite number of pieces of time. And they didn't understand the fact that you could add up an infinite number of pieces of time, and they would simply say, isn't that infinity, right? Because 1 second plus 1 second plus 1 second is infinity. It'll never end. So how do you shoot people? Well, if I had a 1 by 1 object, right, and then I cut it in half, so if this is 1 by 1, and then cut that in half, 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 and cut that in half, and cut that in half. What's half of a 1 by 1? Half. What's half of a half? A fourth, an eighth, a 16th. This shape, if I do it forever, is never going to get bigger than what? 1. So that'd be, why is it that, well, I could, if it was a half second, a quarter second, an eighth second, and a 16th second, it's going to take 1 second. So obviously the arrow is going to get there. It only takes a second. That was the struggle that people had. Do something an infinite number of times, but, well, 1 plus 1 plus 1 is infinity. Yeah, but a half plus a fourth plus an eighth plus a 16th is 1 if we do this forever. Why? Well, there's that shape. It proves it right there. Not only that, if we ever stop, what's this? It's 1, the entire thing, minus a 16th. Why does it have to be a 16th? Because, well, that's a 16th, and it's half of what was there. It was half of an eighth. That's why it's 1 minus the one before. It's everything minus that. Is everybody okay with that? So this geometric shape really just simply gives us everything that we want. That's the nice thing about geometry. It's a physical thing that we can hold and see and say, oh, that makes sense. All right. Prove it using induction. Here's the fun part. This here would be the proof, right? Graphically. Just that picture, I would consider that's a geometric proof. That proves it immediately. But we're not going to do that. What's the basis? What's P of the first element? Well, what's the smallest element? N equal 1, right? So what about n equal 1? What's the left-hand side? That's not equal, so it denotes. What's the left-hand side? 1 over 2 equals 1 minus 1 over 2. Is that true? That's true. Which is what? You cut the square in half, half below, half above. If you have half below, what's left over? 1 minus a half? Still a half? Okay, inductive. I'm going to assume P of the kth what are we going to use for the kth? We'll just simply, the easiest way to do that, let's just simply call it n equal k. For this particular problem, I'm going to let n equal k. Sometimes this is more awkward, but it's nice that it ends up being nice like that. But what does that denote? 1/2 plus 1/4 plus everything up to 1 over 2 to the k does indeed equal 1 minus 1 over 2 to the k. What do I want to show? What's your goal? Normally you don't write this down. I'm supposed to show P of the k plus first, but that means what? N is equal to k plus 1. What does that denote? 1 over 2 plus 1 over 4 plus 1 over 2 to the k plus 1 is supposed to be equal to 1 minus 1 over 2 to the k plus 1. That's what I want to show. What do I have? The inductive hypothesis. Two approaches. Take your equality, add things to both sides until it becomes what I want, or take the left-hand side of what you want, replace things with their equal until the right shows up that I wanted, that 1 minus 2 over 2 to the k, 1 minus 1 over 2 to the k plus 1 actually shows up. All right, last class we did expression. We started off with a 1, we started replacing things with their equal. What I'm going to do is I'm going to start off with the inductive hypothesis. All right, so yes, 1/2 plus 1/4 plus 1 over 2 to the k does indeed equal 1 minus 1 over 2 to the k. What is the only thing that this left-hand side of the equality is missing that this sum has? A 1 over 2 to the k plus 1. It's just the next term, right? So what should I do? Just simply add it to both sides. Is everybody okay with that? I'm allowed to do that. I can just add things to both sides. Is my left-hand side done? This and this are equal, right? That's fine. The left-hand side is done. What's not done? The right. My right is supposed to have two terms, 1 minus 1 over 2 to the k plus 1. What do I have? 1 minus 1 over 2 to the k plus a 1 over 2 to the k plus 1. Okay, how would you put those two fractions together? A common denominator. What's the common denominator? A 2 times 2 to the k, right, which is 2 to the k plus 1. So I could just take this guy here. So I have my 1 over 2 plus my 1 over 4 plus everything over 1 over 2 to the k plus 1 equals 1 minus a 2 over 2 times 1 over 2 to the k plus 1 over 2 to the k plus 1. Everybody okay with that? That's just a 2 to the k plus 1. So what do I have? Minus 2 plus 1, that's a negative 1. Negative 2 plus 1 is negative 1. And so what do we have? 1 over 2 plus 1 over 4 plus everything up to 1 over 2 to the k plus 1 equals 1 minus 1 over 2 to the k plus 1. So, true. We're done. That was taking a equality, doing things I'm allowed to do until the second equality showed up. And since the first was true, this must be true. Does that make sense in terms of algebra? Because this is true, this must be true, because I just simply added the same thing to both sides. This must be true, because I know how to do arithmetic and algebra, and therefore the last thing must be true. They were all true, so we're good. I wanted to show that that last equation was true, so we're fine. Is everybody okay with that? Your choice. You want to show something is equal to something else. You have two techniques. Start off with things that are equal. Do things that are tautologies until you get to an equality that you wanted. Or this left is supposed to be the right. So start off with the left. Make it equal to, start replacing things that you're allowed to replace until it becomes the right. Those are the two approaches that you're allowed to use. All right. Let's try a number theory example. What if I want to show that 3 can divide n cubed plus 2n for n equal to 1, 2, 3, etc. That's kind of surprising. Take an int, cube it, add twice that int, it's always a multiple of 3. That's what that says. Well, what's 1 cubed? 1 plus 2 times 1. 3. Hey, 3, that's a multiple of 3. Let's plug a 2 in. What's 2 cubed? 8. What is 2 times 2? Just to make sure I did this problem right. It's 4. Yeah, 12. So, yeah, we're good still. But does that prove it? Let's do the 3. 3 cubed. 27 plus 6, 33. That's the, all right, hey, look, it worked for 1, it worked for 2, it worked for 3, we're done. No. Because it could break eventually, right? I mean, I can't just simply do all of them at the same time. So, all right, what do I do? Let's try induction. Basis. Obviously, P of the first element is simply P of n equal to 1. What does that denote? Is it true that 3 divides 1 cubed plus 2 times 1? True. 3 divides 3, right? So is it true for the first one? Inductive. I am going to assume that P of, for n equal to k, which denotes what? 3 divides k cubed plus 2 times k. I assume this, that if I ever see a k cubed plus 2k, 3 divides it. Now, what's your goal? Show P of n equal to k plus 1. What does that denote? 3 is supposed to divide what? K plus 1 cubed plus 2 times k plus 1. That's my goal. 2 approaches. Start off with the inductive hypothesis. 3 does indeed divide this, and then somehow start tweaking it until the bottom thing shows up. That sounds hard. How about I start with the bottom thing, and then somehow use the inductive hypothesis to make it, oh yes, this is divisible by 3. So what of the bottom would I start with? I would start with that, right? So that's, if I wrote it as an equality, what is this? This is k plus 1 cubed plus 2 times k plus 1 is equal to 3 times some int, right? I'm not going to worry about that, right? I'm just going to say, okay, I'm going to take k plus 1 cubed plus 2 times k plus 1. What is that? Well, all right, what do I have? I have the inductive hypothesis. What I have is, if I saw a k cubed and I saw a 2k added, I would know that is divisible by 3. Do I have a k cubed and do I have a 2k? Yes, with some extra stuff. But how do I get it? Multiply the entire thing out, and we'll take that to the side and then the extra stuff and see what we get. What is k plus 1 cubed? Plus 3k squared plus 3k plus 1. Everybody know how to define the coefficients of a binomial expansion using Pascal's triangle? Everybody nod your head, yes, I remember my algebra. All right, no, okay. Plus 2k plus 1. Yep, 2. Yay. Thank you. That would have made life very difficult. All right, do I have my k cubed plus 2k? What's everything else? Unwanted. What's everything else? 3 times something. Guess what? Everything else is a multiple of 3. You know, what do I have? I have k cubed plus 2k. I have 3 times this k squared plus k plus 1, right? Hey, look. 3 divides k cubed plus 2k, right? That's the inductive hypothesis. And 3 divides that 3k squared plus 3k plus 3. If 3 divides this and 3 divides this, does it divide their addition? Yes. Therefore, 3 divides the original. K plus 1 cubed plus twice k plus 1, hence we're done. Divisibility statement. If 3 divides the first and 3 divides the second, 3 divides any linear combination of those two. Just add them. And we get the original. Now, how would I have had to have done it the other way? To do it the other way, you would have had to do this. You know what? I'm going to start with k cubed plus 2k, and then I'm going to add 3k squared, 3k, and a 3. And you would ask, why in the world would you want to do that? Because I know in the end I'm going to get this k plus 1. That would be kind of like hard. You would have had to done the backward reasoning to understand to even do that. So the best approach on this one is just to simply start with where you're at and then use the inductive hypothesis later. Don't start with the inductive hypothesis and add things to it because you don't know what to add to it. Isn't that kind of interesting? So any int cubed plus twice that int is always a multiple of 3. No matter what. And I've proved it. Well, what about 101? Induction's done everybody, so we're done. We don't have to show that. I just know it's true. All right. So all these have used weak induction. Let's try a problem that uses strong induction. The inductive hypothesis for strong induction is to assume P of the first and P of the second and everything up to P of the kth. Not only do I assume P to the kth, I actually go ahead and assume everybody up to it. Normally when we're going to be using strong induction is the kth doesn't lead to the k plus first, but some combination down below does, like a k minus 3 does. Right? I don't need the next, I don't need the one right before, I need one certain amount ago. A classic problem of this would be a stamp problem. Let's say you lived in a world of, we have $3 bills and $5 bills. So if you live in $3 bill world and $5 bill world, how much money can you give people? Any combination of 3s and 5s. And so what would be money amounts? Would be what? 3, 5, 6. Could I do 7? No. Could I do 8? Could I do 9? Could I do 10? Could I do 11? Can I do a 5 and a 6? So I can do a 11. Can I do a 12? Any guess? From A on, all numbers are possible. Because what's 13? 10 plus 3. Right? From 8 on, all numbers are possible. Right?
Why haven't we been doing this?
We could have less money. Well, all right. In general, this is the way it works. If I give you P dollars and Q dollars and the GCD of P and Q is 1, then what we can do is we can make, if you're ever curious about what's happening, you could make any amount greater than or equal to p minus 1 times q minus 1. The GCD being 1 is necessary so that you get a plus 1, plus 1, plus 1, plus 1, plus 1 eventually. If the GCD was 2, your eventual numbers would always be 2 apart. You could never get 1s apart. They would always be, the best you could do is a plus 2, like a 6, 8, 10, 12. You would never get 11 or things like that if the GCD between the two numbers was 2. If the GCD was 5, the best you can do is multiples of 5. All right? So what that tells us, like when we look at this, so if I gave you a $5 bill and a $7 bill, those are relatively prime, that means I can make any types of money for what? If it's 5 and 7, it would be 4 times 6, which is, so 24 on. 24 on to infinity, I can give you only $5 and $7 bills. All right, that's the general thing that happens. That's how I make these problems up. I pick those things. All right, but now here comes the fun part. Ignoring this, could I at least prove this? The reason why this will be strong induction is for weak induction, my basis would be 8, right? Because that's the first one where it's any amount of money. So my basis would be 8. But then, because I could do 8, tell me how to get to 9. Well, 8 has a 5 and a 3. How would I get to 9? Well, if I took away the 5, that's a minus 5, and then added 2 3s, that's a plus 6, that's a plus 1. Now I'd be at 9. But 9's 3 3s. How do you get to 10? Well, if you have 3 3s and that's a 9, to get to a plus 1 from 9, if I took away the 3 3s and replaced them with 2 5s, get a little complicated? Right? You'd have to think of this special way of taking and giving. On the other hand, what if I simply did this? If my basis is 8, 9, and 10, how can I get to 11? How about you take 8 and add 3? Well, how do I get to 12? How about you take 9 and add 3? How do I get to 13? Take 10 and add 3. Well, then how do I get to 14? Well, that's 11 plus 3, but that's 8. So take an 8 and add 2 3s. In other words, a block size of 3, how do you get to everybody from that point on? Add $3 bills. Once you're at 8, 9, and 10, just start using 3s. If you just start using 3s from this point on, all monies are possible. So what's your basis? 8, 9, and 10. And then what's your rule? If I'm 3 short, add a 3, and I'll get to the next number.
I guess that answers the question why we're not doing this.
Yes. Well, I mean, it would actually be this. You can make all money using only $3 bills, and how many 5s would you need at most? 2, right? So what would you have? A big stack of 3s and 2 5s. What can I give you? Anything you want. It's a lot of $3 bills and 2 5s. Of course, if you showed up with $3 bills in America, they flip out. Actually, I heard there was even a place where they arrested somebody for they paid in a $2 bill. It's like there is a $2 bill. They actually called the police. They came in, had them handcuff them because it's like that's the whole. We're accusing this person of passing off fake money. We can think the cop would have been smart enough to at least. Anyways, but you can't. You have to go through. You have to do the rules, and the rules are: please set the person to the side. No, that's serious. That actually happened. Actually happened in Heston.
Isn't it technically illegal to refuse something that's actually legal tender or something?
Well, if you know it's legal, and you just don't want it, type of things. But on the other hand, they really believed it was fake because they didn't know there was such a thing. Not a lot of people do, right? All right, I'm over class. All right, next class we'll prove it doing strong induction, and we'll also do the proof leading up to No, the attendance problem will be 5.1, number 11. And then we'll also finish off the proof for the fundamentals of arithmetic, because it requires strong induction. Yep, coming up. I'd have to look. You have the calendar too. I don't look that far ahead. I know what I'm talking about now.
Huh? Yeah.